The issue today is holy geometry. Some call it sacred geometry. Sacred? What is sacred about geometry? I mean, are we supposed to pray here? What is this sacred geometry? And so, yeah, they have these notions, and I think it comes from people who are deeply religious. They're mystics, way deep inside them, and they want to think of themselves as scientists, as mathematicians, as geometers, whatever. And they come across as, no, I'm a scientist. And what they are is simply deeply religious people. Okay. Well, let me start with where essentially I ended up the other day with just showing what's the problem with geometry. So we have a, oh, sorry, got the wrong one here. Give me a second here. Got the one from the questions at the end of the show. Okay, let me get to the conclusions here. Okay, and so those were conclusions about geometry, essentially. And essentially, mathematical figures are not figures. Okay, that's the arguments I made for the last month or so. Math physics only has itineraries. That's what I showed there. In fact, here's a couple. I'll put it side by side so you see what I'm talking about for those who missed the shows. Okay, point is not a point, a line is not a line. A point is a location, and a line is a bunch of locations, meaning an itinerary. Okay, so we're not talking about geometric figure. So we need to know what a figure is before we do all this. And in geometry today, we have no figures because they're all done with motion, okay, and time. And so a line, circle, etc., a bunch of locations, that's all they are. All math solids are hollow. Okay, not one of them is a solid. The tesseract, which I had here as well, let me show you that. Give me a second here. Tesseract there, you can see, is not four-dimensional. What you see there in front of you is a three-dimensional cube on a two-dimensional platform, you can say. And then the one that they define and describe, you can see it's supposedly some 8 cubes that come out of nowhere, magic wand. And so it's nonsense, okay, because that's not a figure. It's some kind of movie of something, of a cube turning into 8 cubes. That's what that is. No, the tesseract is, if it's a figure, it should be standing still, it should not be moving, and it should look something like the one where it says what they illustrate, that blue double cube or nested cubes that you see there. And that is a three-dimensional, again, 2 nested cubes onto a 2D platform. That's all that is, objectively, okay? You don't have to read more into what you see in front of you. Okay, hypersphere, not equal to 4-dimensional either. As you can see there, it's just a balloon that it's growing. That's all it is. Time is supposedly the 4th dimension that is invoked to make that image there. Torus, a bunch of locations. Okay, that's all it is. Itineraries, and when rotating square, cube, tesseract, or any of those, mathematicians are spinning motion itself, time itself. Okay? Okay, so that's where I started, but again, we have to go back to find out what is a figure. And the answer there is that we have to define what an object is. We have to do that for the purposes of physics, and we do that here. And we need to know what an object is for the purposes of physics. We have to find a criterion. That's the issue, or criteria if it's more than one. And the main two that everybody uses are see and touch. Everybody thinks that an object is that which you can see and touch. They also say that an object that exists is that which you can see and touch. Okay, and so the word object and the word exist are synonyms when they use it like that. And we're saying that no, you can't use see or touch because not all objects can be seen, not all objects can be touched. Whereas all objects have shape. It's the universal property that all objects have shape. Okay, and none of those other ones qualify. You know, it's not an object is not that which has mass or volume or that moves or that what it's made out of. It's not the subject of a sentence. It's not a noun. It's not that which has color or, you know, whatever. Anyway, you want to put that. It's not an object that it's not that which exists. Okay, and some people also say that concepts exist, like love exists. You know, no, not in physics. In physics, only objects can be said to exist, and it's not that which is 3D. Okay, because there are 2D objects. 2D objects have shape, and they're not 3D. Okay, so there's all those are rejected. The only one that we can use in physics is shape. That's the criterion. Now we don't have to define shape because we're only comparing it against the other criteria. Okay, that's why we don't have to define shape in physics. We don't continue defining forever just to please the devil's advocate. All we do is we say, look, we got to choose a criterion. Which one are you going to choose? And when we have to choose a shape, it's the only one that's applicable. All the others fail. You can't use them to define the word object. That's the one we're concerned about, not the word shape. We're concerned about what is an object. Okay? You don't know what shape is? Go to kindergarten, show them a cube, show them a ball of the same volume, same mass, same everything, and ask the kids, what is the difference between these two? And they'll say, it's the shape. They'll teach you what shape is. Okay? So if you don't know what shape is, go to a kindergarten and they'll teach you. Okay? Okay, you must have missed the class. Okay, a person asked then, he says, well, does the Mandelbrot set have a shape? And okay, if you look it up, you'll find an image that looks like the one you see there. And I look at that and say, well, yeah, that has shape. We're done. So if that's what they call a Mandelbrot, and we'll stop there. We won't put anything before or after that. We'll call that a Mandelbrot. We can call it X as well. We say, yeah, X does have shape. Straightforward, we're done. Okay? What's the problem? Well, the problem with Mandelbrot is more or less like the problem with the word shadow. You have to find out what the word shadow means, and you got to find out what a Mandelbrot set is, or means, or stands for. What is this? It turns out that you got to use that equation to calculate points, where to put the points on that image. Okay, that's what that equation is all about. And some say that it's just as famous, or not quite, but at least it's just as important or whatever as E equals mc squared, also, which was attributed to Einstein, which I think it should not have been because that equation existed before Einstein. But, you know, this Mandelbrot, it's got that equation. That's how they calculate each point. Then they take that point and they calculate it again. They just do this iteration, okay, forever. And so the Mandelbrot set is something in motion. So if that's what Mandelbrot set, or just Mandelbrot, if you just want to call it Mandelbrot, means or stands for, that's not a geometric figure. What I have in front of us is a figure. It has shape, and I don't have to do anything with it. I don't have to look deeper into it and find out if it's got little points in between 2 points. We don't care about any of that. We say, does that have shape? Yeah, it's got shape. It's contoured all around. It's got shape. We're done. So that, what's in front of us, does have shape and is an object, a figure. All these are synonyms. Okay, a thing. Okay. Now, what do they say? What is Mandelbrot according to these people? Well, they say something else. This is what they put it in motion, and here you can see a little image of this. Okay, and you can see how this thing is growing. Okay, and what you got to do is zoom in, zoom in, zoom in, zoom in all the way. Okay, and all you do is all day long is just zoom in on this, and you can see these patterns in there. Okay, and so the question is that a geometric figure, what you're staring at? And the answer is no, because it doesn't stop moving. Okay, so here you see it. You see how it's just zooming in all the way forever. That's essentially what they're saying here. That, you know, that's what a Mandelbrot set is. And no, that is the one on the right is not a geometric figure. First of all, because it doesn't stand still. Okay, it's got time involved. It's got motion involved. And an object is not that which moves. It's not that which has time. An object is what you see on the left. That which has shape. Okay, the one on the right, we don't know if it has shape because it keeps moving. We don't know what we're staring at. It's got to be standing still in order for us to determine whether it is a geometric figure. Okay, and then let me show you this. Here it is. There's this description for these kinds of patterns that you see on the right. That says, by the end, the magnification of the original image is 3e to the 2,159 power, right? And yes, that is a 3 with 2,159 zeros after it. To zoom into an image smoothly, you must magnify it exponentially. In this case, the magnification doubles every 1.5 seconds. The human mind has great difficulty comprehending exponentials. For comparison, the width of the observable universe is about 9e26 meters. Okay, so what these people are saying, that you got to zoom in, and that's how you create any of these images. And there's several of these, you know, I mean, that's the Mandelbrot, and that's probably the most famous one. But here you have some other sacred geometries. I call them holy geometries, okay? People make these videos. You can look them up. Those are the titles of the videos. Those are the images, the icons they put out there. And you can see they have all these fancy pictures there that a lot of people like to look at. They're like kind of hypnotized by them. They love to look at this stuff. And, you know, just zooming in into their eyes, and I guess with a little music in the background, they fall asleep, and they say, oh, that was so nice. And you know, some of these have hundreds of thousands and millions of viewers. And not only viewers, I mean followers. You say, well, what do these people have in their minds? Is this just to relax and look at these You can call it art. Is that what it's all about? I mean, what does this have to do with geometry? What does it have to do with physics or science? Is this how it's put forward? Or is it just put out there as art? Is that what all this sacred geometry, this holy geometry is about? Okay? And so, yeah, you know, a lot of these people, they just would like to watch this stuff. And so I call them, you know, these, I say these people are religious folks. They just look at these patterns, they're hypnotized by them. And this is what they like to see. They like to see all these patterns. And that's fine. I mean, you know, if you like art, that's great. I have no problem with that. But, you know, to call it geometry and to say that this has something to do with geometry, with figures, or that this has something to do with science or with physics, absolutely not. This has absolutely nothing to do with physics. You want art? Fine. You know, but why bring it into physics? Why bring it to sneak it in through geometry and say, well, this is geometry. We calculate all this with, or we design these patterns with mathematical equations, and then we put it in motion. We have all this stuff zooming in front of our eyes. Yeah, if you want to hypnotize someone, I guess that works, right? Is that what science is about? You know, again, well, science is about explaining, and this certainly doesn't explain anything. Okay, and this is what some of these geometric figures look like, and they're like the Mandelbrot set that you saw a minute ago, okay? And you can see these are different ones that I've just made a collage of, and you can see how they're just zooming in on all these patterns. So what is this? This is art? Great. You know, he who likes to watch this stuff, fine, you can do this all day as far as I'm concerned, but this has nothing to do with physics. Okay? And so, yeah, I think these people, when they bring it into geometry and they call it geometry, they're kind of trying to sneak it into physics, like saying, oh, I'm a scientist. No, I agree that you're an artist. That I can agree with. I cannot agree that you're doing science by showing me this zoom into this so-called sacred geometry simply because you have an equation that plots the points that make these patterns. And all these Mandelbrot sets and all these images are really what they're doing is they're saying let's take the microscope and zoom in ever higher. And so you go from, I don't know, 1000x microscope to a SEM, to maybe atomic force microscope. You can zoom. Maybe tomorrow we'll invent something more powerful, or maybe some kind of telescope that looks in there. And so all you keep doing is just looking at the fjords, so to speak, and making the fjords more visible, and then you're measuring each little nook and cranny in those fjords. That's what it's all about. And so what does this have to do with science, with physics, or geometry? Assuming you want to introduce geometry as part of physics. You know, again, the part of geometry that belongs to physics is the figure, not the equation, not the relation. What belongs to physics is the figure. The rest belongs to math. And there is no such thing as mathematical physics. Math is math, physics is physics. You want to do math, you want to calculate these things and get entertained by the art. Well, that's one thing. Don't say that you're doing physics or that you're a scientist. Scientist is a guy who explains something. That's why we have to distinguish an explainer from a describer. You know, the guy who goes to the art gallery, he's describing. He's not explaining anything. He's just looking at a picture and saying, oh, it's got the blue here and the red there and this line here and the other one is straight and the other one is crooked. You know, that's the description. Art is worthless as far as explanation is concerned. Okay. So here we have another type of these sacred geometries. It's known as the Koch curve or the Koch, I guess, Koch snowflake. Okay, and here's more or less the description of this, and essentially how you build this thing. Okay, it says you start with an equilateral triangle, and on each side you take a piece that you substitute two pieces that are now longer than the original piece. And for those two pieces, you substitute two pieces that are each longer than the original piece. You do this over and over again. You get the same shape, but now each line has that little triangular bump on it. You break it again and again and again. Each time you break it, the line gets longer. Every iteration, every cycle, you are adding on another little triangle. Imagine iterating that process of adding little bits infinitely, many times. What you end up with is something that's infinitely long. Okay? And notice they use this word infinite. And it says the Koch curve was a paradox. To the eye, the curve appears to be finite, but mathematically, it is infinite, which means that it cannot be measured. Okay? And here you see, again, a dynamic version of the Koch curve, or snowflakes. Let me see if I can get this thing up here. Here it is. Okay, you can see what it looks like. Okay, they like to watch these things. They like to hypnotize themselves with it. So what's the problem I have with some of these things? Let me get myself in here. The problem I have is this notion of infinity. There's nothing infinite about what you saw there. First of all, the word infinite is an adjective. And what these people are trying to say is that they're saying incessantly. That's what they're using. That's the notion they're using, but they're using the word infinite in lieu of the word incessant, or incessantly, the adverb incessantly. And what they're saying is, if you do this incessantly, if you do this over and over again, if you do it incessantly, perpetually, forever, okay, then you're going to get those patterns, and you're going to be, again, looking at the nooks and crannies of the fjord that you're zeroing in or zooming in on. Okay? And you can do this over and over and see more fjords, more little nooks and crannies, and you say, well, you can't measure that. Why? Because it all depends on your measuring stick, how big or how small you make it. Okay? And the more you see, the smaller you make your stick, and within that, you expand that a billion times, and now you got to get another stick to measure the nooks and crannies there, and so on down the line. And so they call it infinitely. Well, the image is not infinite. All objects, all figures are finite. But what these people are saying is that the itineraries are infinite, okay, using that word, meaning that you can walk incessantly around this perimeter because there are more points in between any 2 points. That's essentially what they're saying with all this. So you can find more points between any 2 points that make up the perimeter, which make up really the itinerary around the perimeter of the image in question. And so they say, well, from a mathematical point of view, if you keep putting numbers in there and calculating, well, you can go on forever. It's incessant. Yeah, you can continue putting points or numbers as much as you want. That's got nothing to do with the word infinite, which is an adjective that is used to qualify objects, and there is no object which is infinite. Okay? All objects are finite. So the word infinite for the purposes of physics is an oxymoron. You can only use it with objects. You cannot talk about infinite love, not in science. Okay? You can talk about an infinite table, but there is no such monster as an infinite table because all tables are finite. So an infinite object is an oxymoron because what you're saying is an infinite finite, essentially. Okay? That's what it comes down to. So infinite is a word outlawed in science. You can use the word incessant if you're going to be doing math or talking about itineraries or about incessant motion, perpetual motion, or whatever. You can talk about it moving incessantly. That's one issue. You can't use the word infinite in that context. The only way you can use the word infinite with objects, and there is no such thing as an infinite object.